Sure. There we go. All right, so thank you very much for having me. I'm here this afternoon to talk about some very interesting observations that have been made by LDEX, the Lunar Dust Experiment, on board LADEE, of actually pickup ions in the exosphere. And this is an interesting example, what Jamie mentioned in his 2-minute talk about something you didn't intend to observe when you launch a spacecraft, but actually turns out to be a very interesting and worthwhile piece of science. It's fairly fortuitous. So I'd like to acknowledge my co-authors, Jasper Halakas and Greg Delory, with me at Berkeley, and then Jamie Saleh and Mihai Hirani at Colorado. Just very briefly, as an introduction to the lunar exosphere, one of the things that LADEE is really trying to tease out as a fundamental mission goal is what are the relative importance of production mechanisms for the lunar exosphere, and what are important loss mechanisms. So I've diagrammed them here in a kind of a cartoon fashion. You have things like photon-stimulated desorption or thermal desorption, where photons are able to knock neutrals off the surface. You have micrometeorite bombardment, where interplanetary dust grains will smack into the surface of the moon, and they vaporize not only themselves, but a large chunk of the surface regolith themselves. You also have solar wind sputtering. So charged protons, alphas, even the heavier, highly charged ions in the solar wind will impact the lunar surface, and they'll sputter or knock neutrals directly off the surface. And those are sort of the generally commonly accepted main production mechanisms for the lunar exosphere. And we would like to understand which pieces of those are most important, or how each of these changes. Now, there's several loss processes. A very simple one is genes or thermal escape. If you happen to generate a neutral with velocity higher than lunar escape, it simply runs right away from the moon. You have photoionization, so an incoming photon will ionize one of these neutrals. It then responds to the background magnetic and electric fields in the solar wind or in the magnetotail and is convected away. You can have surface capture if it adsorbs to the surface, or you can have night side sequestration. If the neutral falls onto the cold side and is absorbed, you might lose it until the next time. Now, what I'm mostly focusing on in this talk is the loss channel of photoionization. Pickup ions are a very fundamental and a very handy way of measuring the source, the neutral exosphere that you have in place. So what I'm mostly going to be looking at is how potentially micrometeorite bombardment, but I'm mostly focused on solar wind sputtering, how that input correlates with output from photoionization of the exosphere itself. Now, the way I do this is with the Lunar Dust Experiment. Now, this instrument is designed to measure the micron and even the submicron size dust grain environment around the moon. And it was designed to do this in two ways. For large grains, about greater than about 0.7 microns or so, it individually detects the impacts, and I know that Mihai and his team will talk a lot more about this tomorrow in the afternoon session. But there's also a clever mode for grains that are collectively smaller than about 0.7 microns. They're roughly too small to individually register on the instrument, but if you summed over the entire population that was coming into the instrument, it actually generates an appreciable current. So they built in a mode where they would basically just integrate over all of the current. However, what's surprising, though, is that that's not the only current in space. As this detector is flying forwards, not only do you have dust coming in, but you have solar wind plasma and you have pickup ions from the exosphere itself. And it turns out that LDEX is actually a remarkably good detector of these pickup ions, and it allows us to look at that variability. So what does one of these observations look like? This is a plot that was put together by Jamie Saleh. It shows one orbit of the LDEX instrument around the moon. Here's the night side, so here's the day side where you would expect photoionization of neutrals. And these colors that are shown on here, kind of these little stripes and wiggles, is just a color code for the current that's coming into the instrument. And you'll notice that this very, very high degree of variability. It doesn't really correlate with anything that you would expect in this very, very small dust environment. But what we did go through and show is that these sort of ripples or these changes actually correlate very, very well with what the behavior of the background interplanetary magnetic and electric field is. So at any point when the electric field in the solar wind happens to be pointing right into the bore side of the instrument, you register a fairly large current. When it's pointing away, you don't measure much of any current. And actually, we can back that out, and we can get at what that total current is. So the goal in this study is to use that LDEX data, they have this on almost every orbit that they run, to look at how these pickup ions that are originating from the lunar exosphere respond to the inputs. And I'm going to mostly look at solar wind sputtering and micrometeorite bombardment. By doing this, we're going to build a model of the predicted pickup ion flux, taking all the neutral distributions that we expect are there. We identify and aggregate any of these LDEX periods of pickup ions. We subtract some necessary background signals. And then we can finally get to the point of comparing the output from the exosphere, that's this LDEX pickup ion current, to the model predicted current, and looking at how that scales as a function of the solar wind sputtering and the micrometeoroid flux. Now, the model exosphere that we use, this is mainly based off of work by Menelaos Sarantos in 2012. He looked at a number of these species, all of these various generation mechanisms, and a lot of theory behind this. A lot of these numbers will soon hopefully be updated with actual measurements from the LADEE mission, but a lot of these actually, at first glance, are not far off what LADEE has been measuring. We also include some volatile species, which are still, I would say, kind of a big question mark, and then also the noble gases that Mehdi talked about earlier, including helium, neon, and argon. On each of these sources, whether it's thermal desorption or solar wind sputtering or micrometeor bombardment, they have different spatial distributions. For example, solar wind sputtering is only on the day side where the solar wind runs into the moon, but micrometeor bombardment happens all over the surface of the moon. So we take that three-dimensional model into account. We also include data from the Artemis mission. So the Artemis mission is a pair of probes orbiting the moon simultaneous to the LADEE mission. They're measuring all the plasma inputs. And very critically, they measure the electric field. And I show an example here of one day. And you can see a lot of this variability in the components and the total magnitude of the electric field. And that's responsible for this commensurate variability that we see in the LDEX data. So we fold the entire LADEE time worth of Artemis data into the model so that at any point we know where the electric field is pointing. We know how much pickup ions should be running into LDEX. Now, we can also use the Artemis data to calculate our inputs. Specifically, proton sputtering from the solar wind and alpha sputtering from the solar wind. Artemis is a fabulous monitor of the fluxes that are hitting the moon. The blue is the protons, the red is the alpha, so you can see, depending on the density of the solar wind, the velocity, and actually the relative content of protons to alphas, you can get a lot of structure and how much sputtered neutrals are coming into the exosphere. Interestingly, you can actually get portions where the alpha sputtering is greater than the proton sputtering. But that's probably another talk. We also used actually the average LDEX hourly count rate as sort of a rough proxy for the incoming micrometeorite bombardment. LDEX is essentially measuring the secondary ejecta that's coming back up from this input. So it's a rough proxy, but it's worth including nonetheless. So with all of these inputs as a function of time, including where the LADEE spacecraft is, I can predict at any moment what the model should say the incoming current should be to LDEX. And I show an example orbit here. This is about an hour's worth of data. The gray portions are either where LDEX was off or on the lunar night side where there's no photoionization. But there's a small window of about 20 minutes that's on the lunar day side. LDEX was on, and the solar wind cooperated with us such that the electric field was pointing into the instrument. The black dots that are here is the actual measured LDEX current. And the red dots that I've overplotted is one sample run from the model where we put in all of the Artemis data, we put in our neutral distributions, and it's a remarkably good agreement. It gets this sharp jump up where the electric field points into the instrument, and then this slow decay away as LADEE comes around to the terminator and into the night side. So to first glance, the model is really looking good compared to the data, and the only thing we had to do to this was to adjust it by sort of this factor, and that's just a scaling factor, and that tells us sort of how efficient this solar wind sputtering is. And sort of, there's a little bit of unknown physics in how efficient it is and exactly what the distribution is, but the shape fits remarkably well. So now I can take the 5 or 6 months worth of LDEX data and I can throw it all into the big hopper, and at each time I can calculate sort of what this factor is, the comparison between what the model would predict and what LDEX would actually see, and the data come out to be something that actually looks like this. And what this plot is showing is the relative ratio between what LDEX actually measured and what the model predicted. So that's that factor that I talked about in scaling the LDEX pickup ion current. And I've plotted it here as a function of the solar wind, the neutral sputtered flux, in somewhat arbitrary units. And it covers about 2 decades worth. And that's the amount that the solar wind actually varies over the course of the LADEE mission. Now the solid curve that you see here is this ratio of the LDEX current to the model current in the median, and then I've also overplotted sort of the quartiles, the 25 and 75%, and then the far extremes, the 10 and the 90% values. And what you very nicely see is I've drawn these dotted lines over to help guide your eye, but for high enough solar wind sputtered fluxes, there's actually a very nice linear correlation between the amount of solar wind that's coming in and sputtering the lunar surface and how much pickup ion current that LDEX is measuring. And it's a very nice correlation that we see directly what's coming into the lunar exosphere, the solar wind sputtering, is directly what we're getting out in terms of the pickup ion current. You do notice that for low enough solar wind sputtered values, actually, that curve, the pickup ion current as measured by LDEX, somewhat plateaus and bottoms out here. And what that's probably showing us is that if you turn down the dial of solar wind sputtering low enough, there's obviously other sources, such as micrometeoroid bombardment or thermal desorption, that are generating enough exosphere that you can still get pickup ion current into LDEX. And that's actually a really nice, a really nice hint that solar wind sputtering is obviously not the only process that's in the lunar exosphere. We know that there must be others, and in fact, what this probably is, in some sense, is the fact that, for example, argon is a very dense species in the lunar exosphere. However, it's not very easily photoionized. Being a noble gas, it's not something that's done very, very well. But argon does actually happen to have a fairly high cross-section for charge exchange ionization. So if a solar wind proton that's screaming past the moon happens to slam into an argon neutral, it actually has a fairly decent chance of ionizing the argon. So it's possible that sort of this floor that's here is actually charge exchange ionization of argon. And one of the future tasks to do in this is to pull out all the observations that are sort of in this lower quadrant here and look if there's some correlation between that signal and the spatial distribution of where LADEE is seeing the argon, which is, again, mainly around the dawn terminator. In conclusion, the LDEX instrument, even though it certainly wasn't designed to do this, measures ions from the lunar exosphere through its sort of integrated current channel. And this sort of fortuitous measurement is something that we can make good use of, especially with the inclusion of the Artemis interplanetary electric and magnetic fields. And by doing that, we can find that there's a very nice, clean, high degree of correlation between the pickup ion current that LADEE LDEX is measuring and what we calculate as solar wind sputtering from the Artemis. And it's actually a fairly straightforward, at the end of the day, equation between more sputtering ejects more neutrals into the exosphere. Those neutrals are ionized, and that generates more pickup ion current into LDEX. So there's a lot of future work to dig into with the LDEX current data set. This is really, we just threw the whole thing in and looked at what we got out on a broad scale. But there's a lot of individual observations and measurements that we can pick out and do kind of finer correlations and start to break the data set down into spatially resolved points. So hopefully I'll be able to report about that in future talks. So thank you.
Thanks very much. We have time for several questions for Andrew. Mike.
Mike Scheibel, University of Virginia. Did you take into account the ionized fraction of the solar wind or the sputter ejected at all, and could that help the measurements match up with the models a little bit better?
So the answer to the first part is no. Actually, Rick is the person who's measured this in many ways. That the ionized fraction directly from the solar wind sputtering of the lunar surface is actually really low. It's 10 to the negative 3, 10 to the negative 4 yield. So it doesn't typically, at least I wouldn't expect it to contribute an appreciable amount. That being said, it's always worth a look to go back and look at sort of what that would typically generate into the instrument.
Very interesting work. Would have been nice to have a plasma instrument on LDEX,
Wouldn't it?
on a LADEE, but this is doing the job. So, I just want to mention that Alexander Lipatov has done some hybrid simulations on pickup ion transport around the moon, so that he sees shock structures and things. So it may be interesting to look at that kind of modeling. in correlation, of course, to RMS data.
Sure. Sure. Yeah, I think I've seen a little bit of his work, so it's definitely worth the comparison as well. So.
Diane Wooden?
Diane Wooden, NASA Ames. Can you go back one slide, please?
Sure.
You described the axis at low solar wind,
Sure,
sputtered neutral
down
flux.
here. Yeah.
What's going on kind of just above 10 to the 7 where you kind of have a knee that goes up? Do you know?
This little guy,
Yeah.
I'm running out of data points.
Okay.
Actually, give me 1 second. I think I have this where here we go. So this is the messy version of this, and this is all the data points. And you can see by the time you get to about here, you've actually run out of most of your data set. So the error, the variability out there is kind of on the edge of where the solar wind actually provides you any input.
So again, as the solar wind goes up, the efficiencies of creating the pickup ions goes up, and LDEX then measures an increased fraction of that production?
The efficiency stays the same. I mean, those are the underlying laws of physics there, but you're simply bombarding the moon with more protons, and you're sputtering more neutrals directly off the surface.
The number of secondaries per proton is the same. It's just that the number of protons goes up, and so the number of secondaries goes up as well.
Okay.
Those two things are the same. Okay, that's all we have time for now. Thanks very much, Andrew. And our next